Professor Chen this year on wireless charging system for autonomous drones. The motivation behind this project is that over the years, there's been a rise in automation in drones. So with automation in drones, we can see that the drones are getting applied in different applications. So automated drones are getting applied in drone delivery services, in cinematography and taking pictures, in security, and also we've probably seen today that many theses are also really inspired by drones. So drones give us all these benefits, but the problem with the drones is that they have a very short flight time. And with short flight time, they have a very low range. So a way to improve on the range of the drones is we could just improve the battery power density, then drones can fly longer. But that is a difficult task to do, and there's a lot of ongoing research going on for that. Or we could have wireless charging stations placed in strategic places such that we can increase the range of drones. So for example, if a drone had to deliver some package really far away, we could have charging stations in between where the drone could land, charge itself, and move on. So you could ask why wireless charging stations? It could be any kind of charging stations. The point of wireless is that it's weatherproof. So since drones are performing outside in the fields, so weatherproof is very important. It's also very easy to automate because all you have to do is just land the drone and you start charging. So over the summer, that's what we basically did. We automated a drone that it can fly by itself and it can land on the charging station by itself. We also made a solar-powered wireless charging station. So basically, it takes power from the sun, charges the battery bank, and that battery provides power to the wireless transmitters such that it charges the drone. So this is a close-up look on the wireless chargers. So basically, we bought some cell phone wireless transmitters and receivers, and we just put them in parallel. So basically, we have 4 of them because each one cell phone chargers are not high power enough to charge a drone battery really fast. So we tried to put a few of them together to put a higher power. But it still wasn't high enough because the power was only 12 watts. And with that power level, it would take you 3+ hours to charge the drone. Also, the efficiency was very low, lower than 50%. Also, it was difficult to align 4 transmitters at the same time. And for wireless charging, alignment is very important. So this was a big challenge. So here you can see the old system diagram where we have like a bunch of converters to make the wireless power transmitters work. But so the bottom diagram is what I intend to do. I want to put a simplified wireless power transfer system such that I don't need these converters and I can have higher efficiency, higher power level. So basically my goal for the thesis is that I want to make a wireless power transfer system that's 30 watts. So I can charge a drone battery in 1.5 hours instead of 3 hours. I want to have an efficiency up to 70%, and I want to have a voltage between 11 to 17 volts because the battery charger operates in that range. So outside of that range, it wouldn't work. And I want to have one coil such that I can make the alignment easy. So here's the demo of like how the wireless power transfer system works.
This is my transmitter and this is the coils. So I'm going to turn them apart. You can see that full alignment. It's really good performance. Moving the coil over, you can see the motors spinning a little less, and up, and full alignment again. And I can also go this way. You can see that there's power, and yeah. So depending on my alignment, the power changes.
So basically how the wireless power transfer system works here is that I have a current going through the primary coil, and that induces a voltage on the secondary coil, and I'm basically transferring power from one side to the other. So this is basically how the circuit looks like. I have a battery source, I have a DC power source, and then I make it convert to an AC voltage source through the transistors. I basically switch the transistors really fast at 100 kilohertz. Then I have an LC tank. So basically I can model the coils as an ideal transformer with magnetizing and leakage inductances. And I basically put a capacitor and made it in resonance with the leakage inductance. So I have a short in that LC tank. And so my AC voltage gets reflected through the transformer, and I have another resonant tank on the other side. And then I put it through a rectifier so to get a DC voltage. So basically how I made the transmitter is through this schematic. I have a voltage regulator that can give 5 volts to all my components that operates in that voltage range. And then I have a fixed clock that provides a 100 kilohertz signal. But the clock can't drive the transistors because it can't provide enough current. So I need a buffer in between to make sure I can drive these transistors. And then in the previous schematic, you saw that there was only one capacitor in the resonant tank, but here I put a few. That's because each capacitor has some intrinsic resistance, and I want to lower that resistance, and I want to improve efficiency. So if I put a lot of capacitors in parallel, I can improve that efficiency. So similarly, I have a receiver, which I get the power, and then I put through a resonant tank and go through a rectifier. Then I have a battery charging circuit that should take the DC voltage and then charge the battery, but I wasn't able to get the battery charging circuit to work, so I had to use a commercial battery charger. So this was the final setup. So I have a transmitter, coils, receiver, and then charger charges the battery. I tape the coils together so that I can get most like accurate, not accurate, but like consistent measurement. So like, or else it's really hard to measure because it wouldn't always be the same alignment. Also, it's the best case, so my graphs also look better if I taped it together. So this is the voltage versus power level. So you can see that from 0 to 28 watts, my voltage is in between 11 to 17 volts, because that's what was my target goal. Let's see. Oh yeah, you might wonder that why is the voltage dropping? Because it's an ideal transformer, so ideally my voltage should always be the same. But with higher power, I have more current going through my system, and there's some intrinsic resistance in my system. So as I have higher current, my voltage would drop. So the challenging part is that to make sure it's above 11 volts at higher powers. So here you can see my power level efficiency. So my most efficient point is about 21 watts. But from like about 21 to 30, I have about 60% efficiency. So that's better than what I had previously, but not exactly what I had in goal, but not too bad. Then I tried to untape the coils and misalign the coils and to get the efficiency versus and the output power. You can see that with big misalignment, my output power misalignment really drops. That is expected. That's what happens for wireless charging. But that's not a big problem because for our system, the drone landing is fairly accurate. So at most, it will be 1 centimeter misaligned. So it's not a big challenge. You might wonder that output power is actually like not as high as I showed previously. That's because I untaped the coils for this case and there was no pressure on it, so the coupling wasn't as good. But in a real system, when the drone's on top of the coil, there would be some pressure, so I expect a higher shift in the graphs. And then I move the coils upwards, so to get a vertical measurement. Here you can see that the output power efficiency drops even more when I move this way. But this is also not a big issue because my drone's ideally going to land on the charging station, so there wouldn't be much vertical misalignment anyways. So this is what the final system should look like. I'll have a transmitter, and then instead of the 4 chargers now, it's just 1 coil. So the drone can easily align itself with the coil, and the system looks a little simpler. There's no extra converters that we had previously. So for future work, this battery charger can be removed because if my original intention was to have a working battery charger, but I couldn't get it to work. But if it were to work, that battery charger could be removed and the drone would be a lot lighter and the drone would have a higher flight time as well. So I think that's the most important part for the future work. We could also make the wireless power transfer system in higher frequency. Then it would have more toleration to misalignment. But the problem for that is that I have to sacrifice efficiency. So depending on my goal, depending on how bad my misalignment is, I can change the frequency. Also, another thing we need to do for this system is that we automate the circuitry. Because right now there's no way for the circuit to know that I should start charging now, or because it doesn't know if the drone landed or not. But it's not a very difficult problem. Like, we just have to spend time on it, and it's doable. Yeah, thank you.
On your graph for misalignment, it looks like you're shooting curves in 2 different functional forms. Do you have a feel for why?
Well, power and efficiency are not necessarily exactly related with each other, so I don't expect them to move at the same way.
Do you have a feel for what those forms are?
You mean exponential?
Like linear versus exponential versus quadratic?
Yeah, so output is dropping, like the power level is dropping more exponentially than the other. Yeah, I'm not sure.
It's surprisingly linear.
Presumably it must tail off eventually, it's not across the axis.
Well, yeah, efficiency is going towards more zero, and that's what we're looking at.
So is there any, you said that you can get these charging done in an hour and a half.
Yes.
something like that.
Yeah.
an hour and a half about a time?
Well, for the best case is probably 1 hour, like less than 1 hour. What I've read is that that's not good for battery chemistry. So you could probably do it, but you're probably damaging the battery. So 1 hour is probably the best case.
And how long does it fully charge drone?
Oh, flight.
Fly?
Right now, well, it depends on the weight of the drone. So my drone flies about 30 minutes. But yeah, even the best case would be not that high because the applications we're looking for is like carrying stuff, so it would be probably heavy drone, so 30 minutes. But so yeah, it's still like pretty bottlenecked.
Questions from the audience?
Did you consider ferromagnetic cores for your?
Yeah.
Would that improve efficiency?
For the coils.
Yeah.
I think we chose magnetic wires, but I'm not sure about the material you're referring to. So is that
Right now you have two air-core
Yeah.
solenoids close together, but there could be also a ferromagnetic core to that.
also like put something in? Oh, I see. No, I haven't considered that, but that could improve